Alright, what's up YouTube? It's BeetlePlayer1011, and today we'll be talking about the Gaussian integral. So, the Gaussian integral looks very complicated, and what we have is basically an improper integral, showing the area of e to the negative x squared dx, the integral, the area under that graph of the entire real line, being from negative infinity to positive infinity. So just to get an idea of what this graph looks like, I'm just going to quickly sketch it over here. Now, this derivation will actually be quite short. This will be negative infinity, basically, and positive infinity. I could draw my infinities a little bit better, but it's a bit difficult. These go on forever, obviously. And we have our y-axis here and our x-axis here. Now, this graph is actually very simple to sketch. So at the origin, x is 0 and e to the 0 is just 1. So this is 1. Now as it approaches infinity on both sides, since it's squared, you'll notice that the graph looks something like this, where it kind of approaches 0, but never quite hits it. And this is what the graph of e to the negative x squared kind of looks like. Of course, it's reciprocal on both sides, but let's get into its derivation. So this integral can't be expressed in terms of elementary functions. However, given that this is a definite integral, we can definitely rewrite it in a sense to kind of find that definite value. And so, what we're going to do first, and of course this is going to require quite a lot of manipulation, is we're going to write this as a radical of a square, and you'll see what I mean. So x is obviously equal to radical x squared. So in the same way, we're going to treat this definite integral as a number, because that's what it is. It has a specific value. My infinities are really bad, but we have e to the negative x squared dx, this entire thing squared, and then we take the radical of that, and you'll end up with the same value as this regular integral. Well, it's not regular, but it's anything but. Now, this makes this problem a little bit simpler to solve, and I'll show you why. So when you have e to the negative x squared dx and have that entire integral squared, what that is simply the product of two of the same thing. So I'm going to write it like this, where dx multiplied by that same exact integral from negative, sorry, my infinities are so bad. Negative infinity to infinity of e to the negative x squared dx. Now, here's where we have to do something a little bit interesting, and I'm going to do it in red so you can see what I'm doing here. Having this x squared with respect to dx is really just an arbitrary variable to name a specific thing. In other words, I could simply replace this x, as I will right now if I just cross it out, with a y, and have the same thing done here, just scribble it out, and then replace that with y. I could put any variable here and it'll have the same value. It's simply just a variable in terms of that same exact variable. So, to visualize this a little bit clearly, the area from negative infinity to infinity would be the same if I just switched the label of the axes. If I labeled this y and this x, this area is still the same. That doesn't change. The function itself doesn't change. I would have the same x values in terms of y as I would have for y in terms of x. Understanding that should be simple enough. So what this allows me to do is write this as a double integral. So when I replace the second x's with y's, I'm able to write this integral as a double integral like this, where I've the double integral from negative infinity to infinity. Both of these go from negative infinity to infinity. Let me just write this out. It's a little bit to write out. You have e to the negative x squared multiplied by e to the negative y squared dx multiplied by dy. Now I'm going to do one more thing to make this a little bit simpler. I'm going to combine this. So when you have the same base, you can simply just add the exponents. So we're going to have e to the negative x squared minus y squared. And then if I factor out the negative 1, which I'll do in one step, you'll have negative the quantity of x squared plus y squared. So let me write that out. We have the double integral again from negative infinity to infinity. I wish I could just copy and paste it. That'd be nice. I guess I should use a program for that, or a specific program. But yes, so we have e to the negative x squared plus y squared. Now, the reason why e to the negative x squared can't be solved in terms of elementary functions is because you have that x squared term. We know that the integral of e to the x is just e to the x. If I had an extra x term right next to it, so if I inserted an x over here next to it, I could just use U-Substitution and cancel out the x's. So it'd be nice if I had that, and this is where the next step in terms of manipulating this integral comes into play, and that is converting this into polar coordinates. So I'm going to do this in blue-green at the bottom here. And I'll show you how each term converts into polar coordinates. I won't go through the full math of the dx dy, that could be saved for another video. But I'll definitely show you conceptually why it is equal to what it is equal to. So first let's start off with something simpler. This x squared plus y squared. We know that in polar coordinates, it's just given that r squared is the exact distance from the origin to the point on the graph. So r squared is equal to x squared plus y squared. This is simply just an application of the Pythagorean theorem. So if I draw my x-axes like this, I have an x value here, a y value here, and a point over here. And I have a line here. So, we have this x term and this y term, so the exact length of the entire vector, it really is a vector, is simply just x squared plus y squared, and that value is r. And then this value is theta. This is just simple polar coordinates. Now, the new thing really for anyone who hasn't dealt with converting to polar coordinates is this dx dy term, and that is equal to r d theta dr. And I'll show you why. So this dx dy term is, and I'll do it in a different color, I'll show you on a graph. So this dx dy term, what it is, it's a representation of the area, basically, of a little, so let's say I have a square here, right? The entire area is x, or it could be a rectangle too, so x times y. Now, if I take a really small piece, this little dA, I'm going to get that this is dy, and this is dx. So, each extra dA, this little area, is dy dx. Now, when I go onto the polar graph, what I'm going to do is I'm going to see that what we have here is something a little bit different. So the polar graph works a little bit differently. It doesn't work in terms of Cartesian coordinates where you go numbers across and then numbers down or up. What it does is you have thetas going around in a circle, and then these r's going out radially, to make that kind of circle. So here I'm going to take a triangle, and we're going to make this kind of curved like that. Now, this is going to be part of the curve of a polar curve, and we're going to want to find this little area here. So this is R. Now, this arc length basically is going to be r d theta, and this is just based on like the arc length of any circle. We have the measure in radians. If we look in a circle, in a sector of a circle, if we look here, this length here that of this sector is the degree in radians multiplied by r. So when it gets infinitely small, it just becomes d theta. This is still r, that hasn't changed. Now, I want to find the area in here, right? And we can just multiply the base, which is r d theta, times the height. And that extra little bit is dr, because it's not dr times anything, it's simply just adding r as I'm moving along this way, this small little r. So this area is just r d theta times dr. Now that we have these two equations, rewriting this integral should be very simple, and it'll be in a form that we can solve. So we're going to end up with the double integral. It'll go from, I'll write the bounds in a second. The bounds, a little bit different. We end up with e to the negative r squared, r d theta dr. Now, these bounds go over the entire real line. They go from negative infinity to infinity, the lowest bound to the very highest bound. Now, first we have this d theta term. So the thing about polar coordinates is that it simply goes from 0 to 2 pi. You can imagine this on a circle, right? Go from 0 to 2 pi. So the area of that over the entire theta will just be 0 to 2 pi. So we're going to write those as our bounds for our d theta. However, r can go on forever. It can't be negative, though. R starts out at 0, at the origin as 0, and then it radially goes outwards from 0 to r equals infinity, which is infinity away from the origin. Well, I treated infinity as an actual number there. It's more of a concept, but I hope that makes sense. But now, this is an integral we can solve. And what we're going to do is we're going to take this d theta term and move it to separated from the r terms. And we have 0 to 2 theta of just not 2 theta, 2 pi of d theta, which will just be 2 pi because you know that the integral of a d term is just the range of its bounds. The integral does just give you a range. Now, the other part of the integral we'll have to do a little bit more thinking about. We have 0 to infinity of e to the negative r squared r dr. However, this is a very easy integral to solve via U-Substitution. So I'm going to do the U-Substitution really quickly. It should be something that you can do by yourself. If you can do it, you should definitely skip to the next part of the video. But I'm going to do the U-Sub. So let's let U equal negative r squared. So du, I'm just going to draw an arrow to represent du, is negative 2r dr. Here, let's do that. Negative 2r dr. And so, just by manipulation, r dr, I'm not going to cancel out the r's or anything. I can just take the r dr term and set it equal to negative du over 2. So I can just substitute the entire r dr term for negative du over 2. Just to make our U-Substitution a little simpler. So now with that U-Substitution, what we get is that we get negative 1/2 the integral of e to the u du. I'm not going to write my bounds in, of course, because I switched the variable that we're integrating from. And obviously the integral of e to the u du is going to be negative 1/2 now we're going to substitute the u back in. E to the negative r squared evaluated from 0 to infinity. Now I'm going to switch back to the black color as I get back to the entire integral. And we're close to the end here, so we're going to rewrite this. So obviously 0 to 2 theta of d theta is just 2 pi, because we're going to end up with the integral being theta evaluated from 0 to 2 pi. 2 pi minus 0 is 2 pi. So we end up with this 2 pi times this constant negative 1/2. So the 2's are going to cancel out. We're just going to end up with negative pi. And then we multiply that by e to the negative r squared evaluated from 0 to infinity. So I'm going to rewrite it as a fraction, so it will, you'll kind of see it. E to the negative r squared is basically e to the infinity, or negative infinity. It doesn't matter. And you'll see why. Because anything over an extremely large term will just be 0. And we end up with 1 over e to the 0, because we have to plug in the 0 and we get e to the 0. So what we're going to do is we're going to take the limit basically, because this is still an improper integral. This is just going to approach 0, because we know that the general form 1 over infinity is just 0. It approaches 0 anyway. Now, e to the 0 goes to, or is actually exactly equal to 1. Anything to the 0 power is just 1. So the inside of this quantity is just negative 1. We also get that these 2's cancel out. And so what we get is that pi times negative 1 times negative 1 is actually just equal to pi. And now, here's where we come to our conclusion. Remember that we did this being the entire squared of the integral we were trying to initially solve. So the integral from negative infinity to infinity of e to the negative x squared dx, and the entire thing squared is pi. So we end up with our conclusion, and I'll box it so it's clear. We're going to take the radical of the answer that we got to just get the integral from negative infinity to infinity of e to the negative x squared dx. So we have e to the negative x squared dx, sorry if it's taking me so long to write out, I wish I was a bit quicker, is equal to radical pi, because remember, this is just squares, so we want to take the radical of that to get the actual value. We get that this is equal to radical pi. Now, there are different ways of deriving the Gaussian integral and getting this definite answer, but I prefer using polar coordinates, and I think it's the one that makes the most sense. If you have any questions, leave them below. I hope you like and subscribe, and I'll see you with more content coming soon. I'll come up with a schedule of uploading soon enough. I hope you enjoyed the video. Thank you for watching.